Hi class. In this video we're going to be talking about section 1.2, patterns. And I want to start with this image here. What patterns do you see? Maybe pause the video for just a few seconds, or even up to a minute, and look and see what kind of patterns do you see. And maybe before we fully jump into what patterns do we see, what is in this chart? What do these dots represent? Well, if we look at it, this represents the numbers 1, 2, 3, 4, and so on, all up to whatever this number down here is in the corner. And we start to see some things emerge. So we have 1 as a dot by itself, but then 2 is kind of this stacked 2 dots. And then 4 is 2 of these stacks of 2 dots. And then if we look at 8, we have 2 of these stacks of 2 dots. 12 is 3 of them. But notice that those 3 are in the same arrangement as that 3 and the 3 up top. Or here we have 3, 6, 9, 12, 15, which is just my 3 arrangement in the same shape as my 5 arrangement. Or here we have 4 5s for 20. And then here in 9, we have 3 3s, so we have the little triangles. And let me switch color. We have our big triangle. And then down here for 27, we have 3 of our 9s. Or here we have 2 of these 2 groups of 2 groups of 2. So that's 2 of this square, which is 4, 8, 12, 16. That means that's 32. And here we have a septagon, 1, 2, 3, 4, 5, 6, 7. Times 5 goes all the way up to 35. So this is the numbers 1 through 35. And what this lets us see is our patterns such as our so it shows us our patterns in our factors. So this number here we said what was 4 times 5? Or rather, I'm going to write it as 5 times 4. When we get to multiplication, we'll agree that whenever we see something like this, we'll read this as 5 groups of 4. And so since there are 5 of our 4 pattern copied down there, I call that 5 groups of 4. Because 4 groups of 5 would look something closer to this. So if I have 4 groups, I have a square, and then I have a pentagon at each corner. It's harder to draw normal pentagons, but we would have there, we would call that 4 times 5. So the number system that we work with, and we're going to talk more about that in Chapter 2, when we talk about number systems. But when we see the factors, or the things that multiply together to give us a number, we see really interesting patterns, both numerically when we write out the factorization, but also visually. And then something I'd like to point out, here we have 1 that's just kind of a standalone dot. 3 is 3 of those, but then once we get to 5, oh, that's not 5. That's 7. Let me erase that, right? Because 5 is already drawn on right here. And then we have 7. And then 11. And 13. And 17. And 19. And 23. And 30. Something, 32, 31, 30, 29, 31. So we see this really interesting pattern emerge where the prime numbers have to be, because they don't have groups of a smaller size in them, have to be written in this circular form. But then when we have 2 times this prime here, we see this nifty radial pattern, 2 times 17. So there's 17 of these groups of 2 going around this circle. And so I encourage you to spend a good chunk of time just kind of looking through and looking at these patterns and numbers and see what interesting things jump out at you. Right, so going back to, there are ways that all of us are smart at mathematics. This is one way where people who are visual get a chance to see mathematics in a new way. And maybe if the pictures aren't as obvious to you, go through here and write it as 4 times 5, or 2 groups of 2 groups of 5, right? And so we can think about what that picture looks like and what that tells us in terms of groups, where we have our 6 here times 3, which gives us 18. And so patterns aren't just in numbers, but they're in very literal patterns. And so patterns is one of those things that we don't necessarily think about as being mathematics, but is definitely lumped in, and particularly when we look at pre-K, kindergarten, and first grade standards, patterns is really a heavy part of the mathematics content. And so the directions here say to determine the next figure in the patterns. Well, take a second, and again, I'm going to encourage you to pause the video, is just look and see, how do you see the pattern? What do you see happening? Because there are lots of different ways you could see the patterns, but how do you see it happening? When I look at this first one, I see the 2 on the end and 2 in the middle. Now I see 2 on the end and 4 in the middle, 2 on the end and 6 in the middle, 2 on the end, 8 in the middle, which means the next one would have 2 on the end, and not 2, 4, 6, 8, but 2, 4, 6, 8, 10 in the middle. And then similarly with this next one, so we start with one triangle, and then I see it as that triangle we started with, and we add 2 more, and then I see that previous pattern, we add 2 more, and the previous pattern, we add 2 more, and so if I were going to see the next step of this pattern, I'd see the previous pattern, which has 1, 2, 3, 4, 5, 6, 7. So that's my poorly drawn 7 triangles with 2 more. But you might also have seen this, and so I'll use a second color. It's going to get a little harder to see. But you might have seen it as your original triangle, and then your original triangle plus 2, and then that pattern plus 2, and then that pattern plus 2, and so then you would see it as that pattern plus 2. And notice I kind of flipped that one upside down, but that's okay. And then in the last one, there are lots, again, many ways you can see this, but one way you might see it, and the way that I see it, is I see 1 here at the bottom, and then I see 2, and then I see 3, which means my next one's going to have 4. And then here I have 1, and then below that I end up sticking on 3, and then I stick on 5, which means here I have to stick on 7. 1, 2, 3, 4, 5, 6, 7, and then I'm going to pick a different color. These 5 that are here, these 5, 3, and 1 come along for the ride. There's 5, 3, and 1. And so if we wanted to, we could write this in numbers. Here we have 2 plus 2, 2 plus 4, 2 plus 6, 2 plus 8, 2 plus 10, and so on. Or here we have 1, 1 plus 2, 1 plus, and yeah, I just keep repeating it over and over. 1, 1 plus 2, and then I have my 1 plus 2 plus 2, and then I have my 1 plus 2 plus 2 plus 2. And so if we wanted to write this algebraically using a variable, here we have, if this is our, we're just going to agree that this is our first term, this is our second term, this is our third term, and then we have fourth, and in some we have a fifth. And let's say that this variable we're going to call n. Well, here we have 2 plus 2, 2 plus 2, so we'll call that 2 plus 2 times 1, 2 plus 2 times 2, 2 plus 2 times 3, 2 plus 2 times 4, 2 plus 2 times 5, all the way up to our nth one would be 2 plus 2 times n. Because whatever pattern we're on, the nth one, we'll always add 2 for every step along and those 2 on the outside. And then we have something related but a little bit different, because now we have here, we have 1, and then we have 1 plus 2, and then 1 plus 2 plus 2, so we have 1 plus 2 times 1, 1 plus 2 times 2, 1 plus 2 times 3, 1 plus 2 times 4. And so how does this relate? Well, at 1, we don't even have a term. At 2, we have a 1. At 3, we have a 2. At 4, we have a 3. So the number of 2's we have is always 1 fewer than the step we're on. So here we have, I'm going to write it diagonal because I'm running out of space, but we have 1 plus 2 times n minus 1. And so notice what happens at this first term. If I put n equals 1, 1 minus 1 is 0, 2 times 0 is 0, and 1 plus 0 is 1. And so our pattern holds for 1. And so thinking about Polya's problem-solving process, it's important that we can look back and say, does this still work given the other information, right? Because to find that pattern, I really just used my n equals 2, n equals 3, and n equals 4 patterns. And then I'm going to let the last one to you, but I would say go ahead and try to write it as the sum of 2 different patterns, because that might make your life a little bit easier. Because we obviously have this 1, 2, 3, 4 correspondence, so there's going to be an n, but then you're going to need to figure out the triangle piece. And then, of course, other than just with shapes and patterns in that sense, we can look at lots of numerical patterns. And here it says, identify the 100th term and the nth term. And so when we think about teaching, particularly like multiplication, I'm gonna step back and talk about multiplication and then come back to patterns. When we teach multiplication, we often start with repeated addition. So 3 times 2, I can just do 3 plus 3, or I can do 2 plus 2 plus 2, right? I can repeatedly add. But then when we want children to make the step to doing multiplication either with an algorithm or some other process, we give them numbers that it's laborious to do that. So instead of doing 2 times 5, we might do 2 times 57. And that's going to push them into thinking multiplicatively. And so here, I'm asking you to find the 100th number and the nth, because that's going to push you to thinking beyond just pattern then pattern, because I only give you the first 4 terms. You would have to write another 96 terms to get there. And so let's go ahead and start with, see if we can figure out the pattern. So from 1 to 5, what do? Well, we add 4. 5 to 9, thankfully we still add 4, we still add 4, and so on and so on. So if we go ahead and make a table, n, and then I'll just write value down here. So when n equals 1, our value is 1. When n was 2, our value was 5. When it was 3, it was 9, and when it was 4, it was 13. And so let's try to think about where we see this plus 4. This is 1 plus 4. And here we have 1 plus 2 4s, 1 plus 3 4s. And so just like that middle pattern where we had an n minus 1, we have 1 plus 4 times n minus 1. And now let's check again, does that hold for when n equals 1? N minus 1, 1 minus 1 is 0, 4 times 0 is 0, and we're left with just 1. So that means for our nth term, we have 1 plus 4 times n minus 1. And then if we want to find our 100th term, well, that's just going to be 1 plus 4 times 99, because there will be 99 of these steps where we add 4. And you could put that into your calculator. You get 400 minus 4 is, what, 396 plus 1? 397 is your 100th term. And you're going to see homework like this on My Math Lab. And it's important that you pay attention to whether or not it wants you to simplify. So I think for all of these where the number isn't so bad, it's going to want you to say that that's 397. But on the next slide, I have some that are a little bit inkier, and I think it's going to tell you to go ahead and just leave them in some general form. So here for the next one, we start at 70, and I'm just going to write my n and my value again. So at 1, 2, and 3, we have 120. And so what happens between 70 and 120? Well, we add 50. And then from 120 to add 50, we get 170. And so just like our previous one, we're going to have this n minus 1 term. We're going to get 70 plus n minus 1 copies of our 50. And so whenever our difference, let me get a different color. So when the difference between the terms is constant, we call that an arithmetic sequence. And now I'm giving you this definition for an arithmetic sequence because that is in contrast to what happens in number 3 here. Here we have 1 to 3. We could try add 2, but 3 to 9 is not adding 2. That's adding 6. And if we went to 12, or no, 12 isn't, that would be if it was just adding 3 each long time. But here we have 1 times 3, 3 times 3, and we have 9 times 3, which gives us 27. Now we have 27 times 3, which is 81. And so now it's no longer a constant term, but a multiplication. So here I'll write my table, n, and my value. When it's 1, it's 1. When it's 2, it's 3. And let's go ahead and start writing this as powers of 3. When it's 3, it's 3 squared. When it's 4, it's 3 cubed. When it's 5, it's 3 to the 4th. And so here, it's no longer just a simple addition and multiplication like it was in the first example, but we have our 3 to the n minus first power. Because when n is 1, 3 to the 0 is 1. When n equals 2, we get 3 to the first, which is 3. When n equals 3, we get 3 squared, or 9, and so on and so on. And so when let me go ahead and write this on this next slide. When the difference, or how about I'll call it this time, when the change is a multiple, think about exponents, we call these geometric sequences. So I'll highlight that. So when we look at those successive terms, and it's just a matter of adding on some more, those we call arithmetic sequences. But when we're multiplying by a fixed number each time, that's called a geometric sequence. And so here, in this example, what we have, as I make my screen go black, we have 10, and then we multiply it by 10 squared, and we multiply it by 10 squared, we multiply it by 10 squared, and so again we have that the change is a multiple. Our exponent is increasing. But now, what we end up having, so I'm just going to write n and my exponent, because my base is 10, right? So when n is 1, my exponent is 1. When n is 2, my exponent was 3. When it's 3, my exponent was 5. When it's 4, my exponent is 7. And so what's special about these terms? Well, 1, 3, 5, 7, and the next one would be 10 to the 9. These are our odd numbers. Now, how do we write these as a power? Or how do we take n, our whole numbers, and we map that onto our odd numbers? Well, if we look at 2n plus 1, I claim is one way to see this pattern, but that doesn't quite work. Because if I put 1 in there, I get 3. If I put 2, I get 5. If I put 3, I get 7. If I 4, I get 9. But then I'm missing my 1. So I can't do a plus 1. I can, however, do a minus 1. So what I have here is 2n minus 1. When n equals 1, we get 2 minus 1. So let me go ahead and write another column, or another row, and this is our 2n minus 1. And I'm going to go ahead and erase this one here. So this is my 2n minus 1 row. When n equals 1, 2 times 1 is 2 minus 1 is 1. When n equals 2, 2 times 2 is 4 minus 1 is 3. When n equals 3, 3 times 2 is 6 minus 1 is 5. 2 times 4 is 8 minus 1 is 7. And 5 times 2 is 10 minus 1 is 9. And so you can either file away that 2n minus 1 or 2n plus 1 if we start at 0. That gives us our base, or our exponent for our odd numbers. And so 2n minus 1 gives odd numbers, which means that our nth term is going to be 10. So let me see where I want to write this. I'm going to erase some things, okay? So 2n minus 1 gave us the odd numbers, and my nth term is 10 to the 2n minus 1. And then it also asks for the 100th term. Well, that would just be 10 to the 200 minus 1 is 199, and that's a 1 with 199 zeros after it. And so this is an example of why on my math lab, once you get to these sorts of complicated examples, or not complicated, but perhaps more complex, it's not going to ask you to simplify them because nobody has time to type 199 zeros. Like, that's just, nobody has the time. And then we have one more example that's worth looking at. And this one, in many ways, reminds me of that triangle example. Because we have something that's sort of fixed. We have this 193. It goes along for the ride. So we know at the end, our nth term is going to be 193 plus something, right? But then if I look at this here, I have a 2 to the 30th, a 2 to the 30th, and a 2 to the 30th. And so that's also going to be coming along for the ride. And so all we really need to track is what's happening to that middle term. And so let me pick a different color. 7, 8, 9. The next one would be 193 plus 10 times 2 to the 30th. And so let's go ahead and make our table. Our n and then our term. When we have 1, we have 7. 2, we have 8. 3, we have 9. 4, we have 10. And so for our nth term, what's the difference between 1 and 7? 6, 6, 6, 6, n plus 6. And so we have our nth term is 193 plus n plus 6 times 2 to the 30th. And then once the 100th term, 193 plus 106 times 2 to the 30th. And again, you wouldn't want to multiply that out because 2 to the 30th has an alarming number of digits. Because if we look at our powers of 10, we have 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24. That's only 10. So we have 1024 times 1024 times 1024. And here I'll find out what that is. 1024 times 1024 times 1024. It is 1,073,741,828. Here, I'll write that for you. So to save ourselves all the headache, so that 100th term is 1,073,741,824. You can go ahead and leave it in this unsimplified form. So we can look at patterns in shapes, we can look at patterns in numbers, but we can also look for patterns in operations. So here we have 14 plus 15 plus 16, and it says the sum is 45. And then I have 19 plus 20 plus 21, whose sum is 60, and 99 plus 100 plus 101, whose sum is 300. So the question is, do you see any patterns? You need to pause and take a second to look at this. Do you see any pattern between the sums and some part of these sums on the left? So something that I notice, and it's perhaps most obvious to me at this 100, that's 300, and then, well, 3 20s is 60, and 3 15s is 45. And so it looks like the sum of any 3 consecutive numbers is 3 times the middle number. But how do we know? How do we know that that's always true? I've given you 3 examples, and you might try 1 plus 2 plus 3, whose sum is 6, which is 3 times 2. So it seems pretty likely. But how can we know? So I want to give us some definitions. So this statement that I've given you here on the previous slide is called a conjecture. That is a statement or conclusion that hasn't been proven. So I haven't proven to you that that's true, but I've kind of told you that's the case. And then a justification is some sort of evidence. And so I gave you at least 4 examples. And so I'm feeling pretty confident this conjecture is always true. And so that kind of elevates its status to a claim. And I'll have this on the next slide. But like our claim is that the sum of 3 consecutive numbers is 3 times, that's not an S, 3 times the middle number. And then a proof, and I know that proof is this loaded kind of scary word that kind of, we think of maybe back to geometry if you had these 2-column proofs where you had statements and evidence for them. But a proof really is just using definition, terms, axioms that are assumed to be true, and other things we've proven, together with logic to prove that our conjecture is always true. So here it says, claim. The sum of any 3 consecutive numbers is 3 times the middle number. And now let's walk through a proof of what this looks like. Well, it says, and then we're going to think of Paulia's 4-step process. And in fact, the next couple slides I'm going to look at those, but I'm going to talk about them out loud here. So first is make sense of the problem. The sum of any 3 consecutive numbers. So we can't just use specific numbers, but we need to think generally speaking. Well, so here, n plus 1, and n plus 2. So like if n was 1, we'd have 1, 2, and 3. Or if it's 10, we'd have 10, 11, 12. Or 100, 100, 101, 102. So n plus 1, and n plus 2 are 3 consecutive numbers. Right? And then the sum, their sum, is n plus n plus 1 plus n plus 2, which is n plus n plus n plus 1 plus 2, combined like terms, 3n plus 3. And so the fact that it was like 3 times the middle number, and I have some 3's, again, has me feeling pretty good. And we can factor this out using our our distributive property. 3 times n plus 1. Now, where have we seen n plus 1 before? Well, n plus 1 is right here. And what is n plus 1 in relation to these 3 numbers? But n plus 1 is the middle term. So, for any 3 numbers, their sum is 3 times the middle number. And so we'll think again through Paulia's process. So understand the problem. What did we know? We knew that there were 3 consecutive numbers, and those consecutive numbers we said were n plus 1, n plus 2, and we knew that we needed to look at their sum. Look at the sum. Then our plan was kind of, well, let's see what we can get by taking this sum. Well, once we added them together, we saw 3n plus 3. And we knew our claim said that it was 3 times the middle number. And so we wanted it to look like 3 times something. And so we carried out our plan, and we ended up getting 3 times n plus 1. And when we look back, we were like, ah, look at that. N plus 1 was that middle term. And because all we had done in those steps was to find our numbers, taken their sum, combined like terms, and added them together, we didn't make any mistakes. And that was exactly what we wanted to show. And so we were able to look at that result, back at the answer, but then it says, can you think of another way to find a solution? So here's a pretty typed version of that proof we just did. But what if instead of doing n plus 1, and n plus 2, we looked at the three consecutive numbers as n minus 1, n, and n plus 1? Do you agree now, like if n were 2, we get 1, 2, and 3. And if it were 10, we would have 9, 10, 11. And so now they actually look like that initial table where we had our initial claim of 14, 15, 16 was 45. And what was the other one? It was 19, 20, 21 was 60. And 99, 100, 101 was 300. So let's kind of see if we can mimic this proof, but using different names for our consecutive numbers. So the sum of these three numbers now are n minus 1. I'm going to put parentheses around them just to start. N plus 1. Well, that's the same as I'm going to put all the n's together and all the other ones. So n plus n plus n. We have a minus 1 and a plus 1. Well, that's 3n. And negative 1 and plus 1 are 0, so they cancel. And now, just like we did last time, what's our n? It's our middle term. But n is the middle term. And maybe not but, it's more like and n is the middle term. So the sum of three consecutive terms is 3 times the middle. And so you can see how this starts to, in some ways, harken back to what we were looking at in our previous video with our, or no, maybe it's 2 videos ago, our general problem solving. Nope, I changed my mind, it was last video. Where we're looking at general problem solving, where we can relate things to similar examples. And so, just because we switched how we were referring to the numbers as n, n plus 1, n plus 2, or n minus 1, n, and n plus 1, that argument in the middle of taking their sum, showing it's 3 times the middle, and coming to our conclusion doesn't change. And so something I want to point out, right, or really emphasize, is usually there's more than one way to proceed. Sometimes we might prefer one way because it's shorter, right, where we don't have to do as much work. Other times we might like a process because it's clearer. And so we might say that this process is better, not more correct, but better because that initial table had 19, 20, and 21. And that's exactly when n is 20, what we see here. Whereas if the previous example, when n was 20, we would see 20, 21, and 22. So we might argue that we like that one more. But really neither of them is better. But I do want to point out a convention. Mathematicians have lots of conventions with lots of abbreviation things. But this down here, this black square, and I'll even switch my marker to black, is just a square shaded in. And that's like, you can think of that as like a super period. Like, it's like, my proof is done. And so since n is the middle number, the sum of 3 consecutive numbers is 3 times the middle number as desired. And then we put our satisfying, I had my undergrad professor called it a satisfying black square. Because sometimes proofs take a lot of time to get through, and it's really satisfying when you get to the end and you can put that blank box. And so just know, conventionally, we put a black box at the end of our proof. So let's look for another pattern. So here we have some x's and y's. I have positive numbers, negative numbers, some fractions. I have the square of x and the square of y. And then I have my x squared minus y squared. I have an x plus y and x minus y. And then I have an x plus y and an x minus y multiplied together. Do you see any patterns within this table? Do you see any columns that are the same? Like, so interestingly, we see this y squared is equal to this x minus y, but that doesn't hold for any of the other columns or any of the other rows in the table. So that's probably not the way we want to start. But maybe pause and look. Look for, are there any patterns you see in the columns? Well, I noticed that we have a 65 and a 65, a negative 187, a negative 187. This matches this matches this, those match, and those match. So it looks like, based on these 6 examples, that x squared minus y squared and x plus y times x minus y are the same. But again, so this is, if I want to call this a claim, so claim x squared minus y squared is the same as x plus y, x minus y. And I'm actually going to put that into a little bit more words on the next slide. So my claim is, if x and y are any two numbers, and they can be any two numbers, then the difference of the squares of the two numbers, x squared minus y squared, is equal to the product of the sums of the roots. So that's x plus y, and the difference of the roots, x minus y. Right, because if I look at x squared is really x times x, and y squared is y times y, what we get is x squared, so our proof is x squared minus y squared. And now we can think back to some algebra or pre-calculus whenever we had this, and what we end up seeing is that x minus y and x plus y, when we would multiply those out, we get x squared plus xy minus xy minus y squared. And we have xy minus xy, and that's our x squared minus our y squared. And so in words, and this is a lot of words more than algebra, but if we use our distributive property of multiplication over addition, we have that x squared minus y squared is x minus y times x plus y. Now x plus y is the sum of those roots, and x minus y is the difference of the roots, and hence the difference of the squares of two numbers is equal to the product of the sum of the roots and the difference of the roots. And so, again, we have that satisfying black square. In this case, a satisfying green square. When you're writing on a chalkboard, it's a satisfying white square. In any case, we want to draw a square. Let's see if I can get that little record thing to pop off. There we go. Now I have another claim. For any natural number n, 1 plus 1,141 times n squared is never a perfect square. Well, if I put n equals 1, I get, and now perfect square just means that it's some number squared. So like 4 is a perfect square. And we have 9 as a perfect square. 4 squared is 16. 5 squared is 25. Oh, if I could write those in the correct way. 25. Sometimes struggle. 25. 6 squared, 36. and so on and so on. So this says for any natural number n, this pattern is never a perfect square. Well, let's start with a table. N equals 1, and then our n, 1 plus 1141 n squared. Well, this is 1142, and then that's not a perfect square. You're going to have to either trust me or type that into your calculator and take the square root of 1142. If you do 2, we're going to get a bigger number, and I'll multiply that out. 4 times 1141 plus 1. Here we have 4565. And if you take the square root of that, it's not going to be a perfect square. If you take 3, it's not going to be a perfect square. 4 is not going to be a perfect square, and so on and so on. So it feels like that's probably true. But it turns out it isn't. And the smallest number for which that doesn't work, if you let n equals 30 septillion, 963 sextillion, 385 quintillion, 322 quadrillion, 765 trillion, 657 billion, 197,397,208. That's a big number. If you square it, then multiply it by 1,141 and add 1, it will be a perfect square. So sometimes our hunches are incorrect, which is why we need to prove them, where we need to try to proceed through a proof showing sequentially why it works, and then see what happens when we do. And so an important distinction or important point that I want to bring up here is when proving something true, we need to show it works for every single case. That's why when we were looking at the sum of 3 terms, we had used n plus 1, and n plus 2. But when you want to disprove something, or show that something is false, so disproving, meaning false, you only need a single counterexample. So even though our claim was that this is never a perfect square, because I showed you one case where it is, I know that my claim is wrong. We know that this is false. It's just it needed to be a really high number for us to get there. And so to wrap up today's ideas was really thinking about patterns, and we could think about patterns in numbers. We could look at patterns in shapes and those kind of building up of shapes that we saw there. We could look at patterns in a sequence of numbers. We could look for patterns in sums of numbers. And we introduced what a proof was. So a conjecture is something we haven't proven. A claim is something that we're pretty sure is true. And then we have to give evidence in form of a proof to show that it works always. If we want to prove something is true, we show that it works for every case, generally speaking. That's why we used our variables n in those 2 proofs. But if we wanted to show something was false, we only need a single counterexample. There were a couple other terms around sequences that I didn't include here in the recap, but you'll have those on the previous slides. And so I do this here because I want, in our next couple videos, once we get to chapter 2, we're going to be talking about logic and formal argumentation and proof. And this, I think, is a relatively approachable introduction to a proof. And make sure whenever you finish your proof, you don't forget your satisfying black square. Have a great day, everyone, and I'll see you in the next one.